This is a dual nature MCQ from NEST 2016, question number 10 from that PDF. In an experiment on photoelectric effect, photons of wavelength 300 nanometer eject electrons from a metal of work function 2.25 electron volts. A photon of energy equal to that of the most energetic electron corresponds to the following transition in the hydrogen atom: N2 to N1 state, N3 to 1 state, N3 to 2 state, N4 to 3 state. Again, this is a mixed concept MCQ because it borrows concepts from Bohr model of hydrogen atom, right? And of course, dual nature of radiation matter because photoelectric effect is there, which is in particle nature of radiation. Okay. Okay. So we are given a photon of wavelength 300 nanometer, and it is ejecting electrons from from a metal of work function 2.25 electron volts. Okay. And also there is a term called most energetic electron, which means we have to use the maximum kinetic energy formula, which is h nu minus phi naught. Okay, I hope you understood this, right? K max is equal to h nu minus phi naught. And what is the formula that we have in Bohr's model? What is the formula for energy? It is negative 13.6 upon n squared electron volts. Raise your hands if you remember that formula. En is equal to negative 13.6 upon n squared electron volts. You have to know this, otherwise you cannot solve the problem, although you know everything about photoelectric effect. Okay. Okay. Observe that keeping everything in electron volts is going to be helpful because this formula is in terms of electron volts. Work function phi naught is also in electron volts, and then that K max is what we need to find. Okay, cool. First of all, this is nu, so let us convert it to, let's convert it to lambda formula. So hc by lambda minus phi naught. Now this is in joules. Okay, this is in joules, hc by lambda, isn't it? H nu. How to convert it to electron volts? Any suggestions how to convert it? Tell me. We know 1.6 into 10 raised to negative 19 joules is equal to 1 electron volts. Okay, so basically if I want to convert anything in joules to electron volts, I must divide by the charge on electron. Correct? I must divide it by the charge on the electron. Let's do it now. Let's do it. Okay, what is it? 6.626 into 10 raised to negative 34 into 3 into 10 raised to 8 upon wavelength 300. Is in nanometers. Yes, so 300 into 10 raised to negative 9 into charge of electron. 1.6 into 10 raised to negative 19 minus phi naught, 2.25 electron volts. Okay, allow me to use calculator. Okay, allow me to use calculator this time. And let us also take the note of this ratio. It could be useful later on. Say around 4.14. Okay, it's around 4.14. You may take it as 4. Okay, let's show it. 6.626 into 3 into 10 raised to negative 34 plus 8 upon 1.6, already considered that, into 300 into 10 raised to negative 28. Okay, Yeah, so basically it will be a multiple of this because 3 will get cancelled, minus 2.25, that's 1.89. Okay, that is 1.89125. I will also put the previous calculation here. Okay. Acha. So that's now 1.89125 electron volts. And now we have to decide which two states will give that transition, right? So let's invoke this Bohr model formula now. En is equal to negative 13.6 upon n square. Okay, now look, this En is actually, okay, let's call it delta E now, delta E, that is 1.89125, and that is a negative 13.6 into 1 upon m squared minus 1 upon m squared. Okay, 1 upon n squared minus 1 upon m squared. So if we divide 1.89125 by 13.6, okay, if we divide 1.89125 by 13.6, we are getting 0.139. Okay, we are getting 0.139, and that will do the job for us. Okay, 0.139 is equal to negative of 1 upon n squared minus 1 upon m squared, or we can absorb that negative sign inside, right? And now what we can do is, instead of calculating it, well, I think we cannot, because one equation is there and two unknowns are there. So let's take the help of the options now. Let's take the help of the options now. Okay, so for option A, let's calculate 1 minus 1 upon 4. That is 3 by 4, definitely not equal to 0.139. Let's go to B. 3 to 1, so 1 minus 1 upon 9, that is 8 by 9, and that is greater than half, so that's also not equal to 0.139. Let us go to option C. 3 to 2, so 1 upon 4 minus 1 upon 9, that is 9 minus 4, so 5 by 36. Yeah, good. This is a contender because 5 into 7 is 35, and 1 upon 7 is around 0.142. Yeah, 0.138. Okay, 0.138. That agrees well with our calculated value, 0.139, but let's also get it for D. 4 to 3, so 1 upon 9 minus 1 upon 16. Let's do it here. 1 upon 9 minus 1 upon 16. 0.048. That's definitely not the case. So which option is right? Option C is right, because the value that we got is matching with, okay, it is matching with option C. Option C.